You're listening to the Max Planck Lawcast, which showcases the academic research currently being conducted across the Max Planck Law Network. I'm your host, Christopher Murphy, and together we'll be talking to some of the more than 400 researchers who are pushing the frontiers of legal knowledge in Germany and abroad. When it comes to new and exciting legal research, the Lawcast has you covered. Well, thank you very much for tuning in to the next episode of the Max Planck Lawcast. In conducting background research for today's podcast, I learned that the sun is not just a big ball of fire, but rather a big ball of fire powered by nuclear fusion. If we could somehow replicate such nuclear fusion on Earth, we'd be able to provide ourselves with a safe, affordable, and clean solution to meet all our energy needs, which sounds pretty amazing, right? To find out more about the potential of nuclear fusion and the legal regulations that we need to have in place to foster its development, I'm joined today by Philipp Sauter. Philipp is a lawyer and physicist who is currently writing his PhD at the Planck Institute for Comparative Public Law and International Law in Heidelberg. Welcome to the program, Philipp.
Thanks for having me.
Yeah, well, so we're talking nuclear fusion, nuclear fission, big topics. I'm just a humble podcaster, so maybe you could begin by providing us with a brief primer of what the difference is between nuclear fission and nuclear fusion.
Sure. So maybe we start with what they have in common. So both are processes that take place in the atomic nucleus. So if we have an atom consists of a nucleus and the shell. In the nucleus, there's protons and neutrons. In the shell, there's electrons. So maybe you're getting reminded of your high school physics class now.
Yes, I'm getting kind of flashbacks, which aren't very pleasant.
Yes. And both processes release the strongest force in the universe. And physicists are very creative, and they call it the strong nuclear force. And actually, this is where it ends, what they have in common. So nuclear fission is the process that we know from nuclear power plants. There we have heavy atomic nuclei, mainly uranium, and we can split that uranium into smaller atoms. So we start with a big nucleus and end up with smaller nuclei. And in this fission process, energy is released, and this energy can be transformed to electricity. However, what is also possible, and you mentioned the sun, this is what happens in the sun and in all other stars, is nuclear fusion. Then we start with small nuclei, such as the light that we have hydrogen and helium. We fuse them together to a slightly bigger nuclei, and this process also releases energy. Fission is we start with a big nuclei, end up with two smaller, and fusion is like the inverse process. We start with small nuclei and end up with a bit bigger atomic nuclei.
Okay, so they're kind of exact opposites of one another. One is
exactly, yes,
is splitting nuclei, the other is fusing nuclei.
Exactly.
Okay. What then are the chief benefits of fusion, or the nuclear fusion then, compared to other energy sources? And I guess particularly would be of interest nuclear, or the comparison with nuclear fission.
Mm-hmm. So this is why I get fascinated all the time, because just to demonstrate the orders of magnitudes of energy involved, just think about a regular bottle of water consisting of, about a liter. Mm-hmm. The hydrogen atoms in that water contain as much fusion energy, roughly as the coal within an entire train full of coal. So burning an entire train of coal, which can be, 1 or 2 kilometers long, contains roughly the same fusion energy as the hydrogen within the water in the water bottle. I think this is the orders of magnitude involved are just so amazing and so incredible. And as I said, we can use hydrogen to get fusion energy. Just to think about all the water we have in our oceans. So there's plenty of energy sources. It's like an inexhaustible source of energy. And the best thing is there are no greenhouse gases involved. So it's an inexhaustible and green energy source.
Okay. Wow. Sounds very impressive so far.
It does. But this is the same what's said about nuclear fission. So we could take a similar comparison, think about, a cube of 1 by 1 by 1 meter of uranium. This also contains roughly about the same energy as a train full of coal. However, we know fission has some downsides. Mainly, it's a safety issue. Just think about Chernobyl, think about Fukushima, the two major accidents that have happened in the last 40 years. and also the waste involved. So the nuclear waste issue is a big, big political topic. We're doing nuclear energy for more than 70 years now. We still don't know what to do with our waste. And the biggest problem is that the half-lives that are involved are so long, we need to take care of the waste for hundreds of thousands of years. And this is, compared to fusion, these downsides don't exist in fusion. So fusion is inherently very, very safe. You don't have the risk of a chain reaction. Why is that? So in fusion, you have to get a perfect equilibrium between different parameters, and you need to constantly put in new particles from outside. You need to manage magnetic fields. And in an emergency situation, you can simply shut off a facility, stop the magnets, stop the refueling of the machine, and there is no risk of a runaway chain reaction.
Okay.
And also with the waste, fusion produces some kinds of waste, but on one hand, the waste produced is way less compared to fission. And there is some kind of radioactivity involved, but the radioactive material was only radioactive for about 100 years, so way more manageable for humanity than these 100,000 of years in fission.
Oh, okay, so that means the radioactive material after 100 years or so is no longer considered dangerous.
Exactly. So,
Okay.
so if you wait 100 years with the radioactive material, you're left with less than 1% of the radioactivity you started with 100 years earlier. And the same process
from fusion.
From fusion, exactly. And fission, it takes hundreds of thousands of years to have the same.
Okay, major difference then.
Yeah.
Okay, and fission also produces more of the said waste than fusion.
Exactly, yes.
Okay. This all sounds super promising, and we have a clean technology in the sense of no greenhouse gases, virtually limitless kind of energy sources. Hydrogen 2 and hydrogen 3, you say?
Exactly. So these are two isotopes of hydrogen. So the hydrogen that we know of is hydrogen 1. And then there are two isotopes, so meaning there are more neutrons in the nucleus, hydrogen 2 and hydrogen 3. And
okay,
yeah.
Right. Great. Sounds awesome. I wonder, though, we have this, you mentioned before, that the sun is nuclear fusion in a big fiery ball there. It's all going on up in the stars. But I assume that NASA is not currently looking at hooking up a 150 million kilometre power line. That's probably not feasible to the sun. So we're going to need to bring nuclear fusion to the Earth another way. Where are we currently at in this regard, and what progress has been made?
So within the fusion scientist community, there's a running gag that says we're always 30 years away from commercial fusion energy, and that is true.
Okay.
So in the 1950s, fusion research started, and back then scientists said, yeah, in 30 years we're going to have fusion energy. And if you ask me today, when are we having commercial fusion energy, I might
another 30 years. Okay. So that's the running fusion gag. Okay.
Yeah. Yeah. Well, actually, it depends on who you're asking. So if you're asking some startup companies, some of them are promising a nuclear fusion power plant running next year. Others say in the late 20s, early 30s. So yeah, of course, these numbers must be read cautiously because these are startup companies. They're looking for investors, so maybe they're over-promising
more capital
the technology.
Okay.
If you ask our colleagues at the Planck Institute for Plasma Physics, which is one of the leading institutions in the world for fusion research, they're saying something in the 2050s to 2070s.
Okay. Which is conveniently also around 30 years away.
Just to give you an overview, yeah, the average is about 30 years, so let's see. Yeah, but there have been huge heard about the National Ignition Facility.
Yes, I think that was in the news a while back.
Exactly. In December, they reached the so-called break-even point because for the first time in history, they produced more energy than they needed to make fusion happen. Because let's get a step back. Fusion occurs at temperatures of around 150 million degrees.
Insane temperatures.
Yes, it's even 10 times hotter than the core of the sun. So these are enormous temperatures. And you can imagine you need a lot of energy to produce this kind of heat.
Yes, yeah.
And also you need, as I said, magnetic fields. These magnets also need a lot of electricity. And for decades now, we try to reach a point at least close to produce the energy with fusion that we put into the first place. And NIF, California, for the first time reached that break-even point and produced actually more energy than they put into the heating.
This was basically the very first time something really big has happened. They've now been able to, and this was the future, so to say, but they were obviously doing it on a small scale.
Exactly. Yeah, also you need to read these numbers also a little bit cautiously because they did it with lasers, and the laser put 2 megajoules as the unit into it. The fusion produced 3 megajoules, so a 50% energy gain. But to produce the laser itself, they needed 200 megajoules. So in the end, it's still almost 100% energy loss. So there's still a lot of fine-tuning necessary to actually have a net zero energy gain.
Right, okay. But, I mean, obviously, mankind is taking big steps here. They're on the cusp of something big if we can manage to pull this off. And let's be optimistic and say it happens within the next 30 years.
Yeah, especially there's also a roadmap set out by the European Union, for example, which has different goals within the next, I think, 30 years. Currently, maybe you've heard about ITER. This is a big research facility currently under construction in southern France. Actually, this was built to show this break-even point in the 2030s. So the Americans overtook us by 10 years. And then after ITER is successful, there's a plan to build a demonstration power plant in the 2040s. And after that is proven successful, then there's the plan for commercial power plants.
Yeah, on the cusp of something big then. Well, I mean, obviously people have been saying that for the last 60, 70 years, but let's be optimistic and say that's the case. So that brings me to a question then about your research in particular, because you're a physicist, but you're also a lawyer. And you're kind of doing your PhD on how this new form of energy, which is a nuclear technology after all, should be regulated. What have you got to say on that matter?
As I said, it's a nuclear technology and it's releasing the strong nuclear force, the strongest force in the universe. So there are some parallelities to fission, also some dangers.
Sorry, I just have to ask briefly, is a nuclear force stronger than a black hole?
Yes, so the black hole works with gravity, and gravity is the weakest force.
Look at me. So, sorry, physics teacher from high school.
Imagine having a fusion reactor the size of a black hole. Oh, this would be a lot of energy would be produced in there.
Okay, so nuclear tech is the strongest force in the universe, well and truly.
Exactly, yeah. Since we're releasing these strong forces, there is some kind of regulation necessary. So we don't need to reinvent the wheel for that because we already have a legal framework. It's called nuclear law. So part of public law that focuses on all the nuclear stuff. And there's an elaborate framework for nuclear fission. And there we talk about the 4 pillars of nuclear law, which are safety, security, safeguards, and civil liability. So, I mean, safety is pretty clear. You want to keep the people and the environment safe from the dangers within a nuclear facility. Security is like the other side of the coin. You also want to keep the facility and especially nuclear material safe from external influences and from external people. Then safeguards is maybe the most political part of it that deals with the question of nuclear weapons, nuclear non-proliferation, where fusion also has some kind of role in it. And civil liability, there is a special legal regime in the case of nuclear accidents, because if you take a look at the Fukushima accident, there were damages in the range of more than 100 billion euros. So to deal with that legally, there is a special regime.
Okay, right. And so this all obviously exists for nuclear fission. And so, yeah, as you say, we don't need to reinvent the wheel. We could apply a lot of this to nuclear fusion as well.
Exactly. Now is the question how to do that. So there are 2 possible approaches that we could follow. The one is to just use the existing framework that we have and apply that to fusion. The second alternative is to actually that what we've done in the last 6 years, look at the specific dangers of that technology and then trying to adapt legal rules to that. And I think a mixture of both would be useful because, as I said earlier, there's ITER, the research reactor currently under construction in France. And when construction started, they asked themselves, so the French regulator, how should we regulate fusion? And they simply applied the existing framework for nuclear fission. And this led to a lot of problems. So this led to increased costs and an increased length of construction because there are so many specificities that need to be followed, such as you are not allowed to drill holes in your wall, which makes constructing way more difficult and way more complex. And so you see, you can overregulate a facility and then the technology, which could actually damage your
Okay.
progress. So you need to find like a good balance between the dangers and
Right, so like a happy medium to obviously make sure it's safe, but not being so strict as to stifle
exactly.
the possible growth of this new industry. Have discussions already then begun on how this should happen? Obviously, you just mentioned the case there in France, where maybe it didn't work out so well, where they just applied the fission laws. Are there any other maybe more positive examples of where they've said, okay, we have this new nuclear force or power here, but it's actually not as dangerous as the one we previously are currently using? Let's maybe support it by not over-regulating it.
Yeah. So there are two countries with a huge startup sector in fusion. These are the UK and the US. And not surprisingly, these are the countries at the forefront of regulating fusion. So the UK already published, I think, in 2021. So 1.5 years ago, a first white paper on regulating fusion. The US is currently working actively on regulation of fusion. And there they try to find the balance that I said earlier on how to have a safe technology without over-regulating it.
Right, okay. So there's certainly an awareness that what maybe went on in France was not optimal and we need to change tact.
Exactly.
When we're talking about this regulation, the way that nuclear fission is regulated, that's an international level, whereas, I guess, coal-fired plants, gas-fired plants, regulated at a national level. What's the difference here, and should fusion be taking the international or the national approach?
That's a very good question. So the first question is, why is there international regulation? So in international law, we've got a group of sovereign states, and sovereign states cannot be forced to follow some kind of convention or agreement if they do not accept that agreement. And especially if we're talking about things that are so close at national sovereignty, such as energy, it is very difficult to convince states to agree to international agreements. Just think about the role of energy in the last couple of months with the rising energy prices, or think back to 2018 with the yellow jackets in France when they protested because fuel prices should be increased.
Yes.
You see, energy is at the heart of national sovereignty, so states are very, very reluctant to agree to international agreements, except there is a specific reason to do so. And within fission, we have the potential transboundary effects.
Okay, so not just one state could be affected by...
Exactly. So I'm too young for Chernobyl, but my parents told me after the Chernobyl accident, they shouldn't buy lettuce in Germany because it could be contaminated by the nuclear fallout. And I think even today you should be cautious in some areas in Europe to pick mushrooms out of the woods because there could still be some kind of contamination. And this is the reason why, especially after Chernobyl, on the international sector, a lot of conventions and agreements and treaties were concluded.
Ah, okay, right. So that actually the international kind of approach was, in a way, spearheaded then after Chernobyl.
Exactly. There are two conventions on the early notification and on assistance in the case of nuclear accident, which were concluded a year after the Chernobyl accident. In the late 90s, there was a convention on nuclear safety. It was concluded with some minimum standards for nuclear power plants. And yeah, so these transboundary effects really pushed fusion and pushed the legal framework for fission. Exactly.
Okay, right. And this would then be probably the approach as well, less, not as tightly regulated, but still an international approach for fusion.
So this is a very good question. So there we need to differentiate. As I said, there are these different pillars of nuclear law. And if we talk about the safeguards pillar, so the nuclear weapons stuff, of course, there is some kind of international regulation necessary because these rules want to stop a country from developing nuclear weapons. So national level wouldn't make sense there. And there is some kind of proliferation potential with fusion, way, way less than with fission, but it still exists. For example, NIF, as I mentioned earlier, the facility in the US, it's a military facility to test simulation codes for hydrogen bombs. And hydrogen bomb is a fusion bomb.
Oh, okay.
And also classical nuclear weapons are regularly boosted with tritium, so the material hydrogen-3, this isotope used in fusion.
Yes.
So 2 to 3 grams of tritium are enough to boost a warhead by the factor of 10 to 100. So Fusion also plays a role in nuclear weapons,
Okay.
meaning that there needs some kind of international approach for that.
Okay. The material doesn't disappear, basically.
Exactly, yeah. And the second question is with the others, pillars like safety and security. There is the question, are there these transboundary effects which make it necessary to have some kind of international regulation? There, most probably it's not too important, because if there would ever be an accident in a fusion power plant, the effects would limit themselves to a couple of 100 meters around the power plant. So from a safety point of view, it's not too necessary. However, if we take a look at commercial interests, then it could be useful to have some kind of international regulation, because it's way easier for a company to commercialize their technology if they only need to have one design which is in accordance with one kind of international safety regulation, rather than, 20 different regulations.
Okay. The USB-C of nuclear fusion.
Exactly. Also, there's the question, what's the appropriate level? Of course, we have the International Atomic Energy Agency, the IAEA, which could be a level, but maybe also the EU could be a useful institution to at least regulate it on the European sector.
Okay. Don't go away, because we're going to have plenty more for you after this short break.
Welcome to Max Planck Law, one of the world's largest networks for legal research, based in Germany. Our world-class institutes invite applications for fully funded PhD and postdoc opportunities in almost any area of law. Join a thriving community of over 400 researchers in an international and interdisciplinary environment. Experience the high quality of life that Germany offers while collaborating with colleagues across institutes, working and writing in English. We provide you with unique specialist libraries, excellent workspaces, and support in developing your research and your academic career. Apply today. For more information, visit law.mpg.de.
Welcome back to the Lawcast. Thanks for listening to us today. Kind of gone from international to EU, and then I'd like to go to national now, because you're in Germany, I'm in Germany, the Max Planck Institute's in Germany, and anyone who's been following the news knows that the last nuclear reactors are switched off. Is there then any possibility, or does nuclear fusion even have a chance here in Germany because of the word nuclear?
That's a very good question. So on the one hand, Germany and the Max Planck Society is one of the leading institutions in fusion research. We have 2 fusion research reactors in Germany, one in Garching and one in Greifswald. The word nuclear has some kind of stigma. Actually, what I think is interesting, in the UK, they only talk about fusion instead of nuclear fusion, because they want to avoid that kind of nuclear stigma, even though the UK is way more pro-nuclear than Germany. But I think that fusion definitely has a chance in Germany, because the potential that fusion has is just so immense compared to the dangers, and there will be some kind of convincing necessary, but I think this will be possible in Germany. Of course, the question will be in which context. So, as I said, we won't have any fusion power plants in the next 10 years. So in the current discussions that we have, like transforming our energy system to carbon-free sources, I don't think that fusion will have that big role in that. However, if we think about long-term plans beyond 2050, I think fusion can play an enormous role. We've just seen the new IPCC report, which tells us it's almost impossible to reach the 1.5 degrees Celsius goal. So there will be the need to reverse some kind of adverse effects of climate change. And quite often it's just a question of energy, often of a lot of energy. But if you have an energy source that is inexhaustible and green, this could help maybe in the future to adapt and to revert some effects of climate change.
Through something like carbon capture? Or
Exactly, carbon capturing, for example.
Mm-hmm. Researching a little bit on fusion, I came across an article that also mentioned that helium-3 is a possible fuel for nuclear fusion, and actually being even more powerful than hydrogen-2 and hydrogen-3. The problem would seem, though, is that this is pretty much not found on Earth, but is in abundance on the Moon. Would that also mean that the nuclear fusion age could also herald in the age of moon mining?
Exactly. So the current plans from most researchers and most startups is to stick with hydrogen-2, hydrogen-3. However, there are some plans to use helium-3. So we know the helium we have on Earth is helium-4. So it's got a neutron less than the standard helium-3 neutron less than helium-4. And the energy produced by helium fusion is greater than that of hydrogen fusion. However, as I said, where do you get the helium-3 from? It does not exist on Earth. We needed to mine that from the moon. However, this is very science fiction-like and also has some legal problems. So there is the Moon Agreement, and the Moon Agreement actually prohibits the commercial use of the moon. So there are a lot of legal implications also, apart from how feasible is it from a technological point of view to actually fly to the moon, get back material, and also that it makes both economic and sense and doesn't need more energy to fly to the moon and back than when it's produced.
Sure, okay. It probably also fits within the 30-year mold of reading books back in the 80s, where we all had moon colonies by 2000. So maybe, as you say, more science fiction. But obviously legal ramifications should it happen at some point.
Yes, definitely.
My final question for you is, I guess, how do you hope that your research will shape the debate on the regulation of nuclear fusion?
Well, I hope that the people in charge of drafting the regulations will read my thesis, that they're listening to me, and maybe that I can inspire the different regulators. I've already been in contact with the IAEA about my current work on the safeguards issue, so concerning non-proliferation, and I hope that I can somewhat shape the future regulation, that when, I don't know, I'm in my 50s or 60s and I stand in front of the first fusion power plant in Germany, I can say, this only stands here because of the regulation that I somehow shaped.
That would be pretty impressive. Yeah, very good, Philip. Well, thanks so much, mate, for coming on today. I really enjoyed this. It was a totally informative discussion. I learned a lot researching for it, and I wish you all the very best for the rest of your research.
Thank you. Thank you for inviting me, Chris.
You're welcome. Bye. Thanks for listening to the Lawcast. If you'd like more information about Max Planck Law, or if you'd like to get involved, please visit us at law.mpg.de.
Max Planck Law. Excellence in legal research.